Thank you, Gordon. I'm very grateful. My talk today is on a new kind of virtual reality display, one that supports the eye's native ability to focus on objects placed at different distances. To understand what a display does, let's start with a lens, one of the main components of any near-eye display. A lens serves to optically place the display at a different distance from the eye. Our work proposes a new kind of lens, one that has the ability to simultaneously focus different parts of the display to different distances. We refer to this design as a Split-Lohmann computational lens. To understand why such system is useful, let's consider how multifocal displays work. A multifocal display creates a 3D scene by placing content at different depths, typically using a focus tunable lens. The focal length of the lens controls the depth at which the content is placed. By rapidly sweeping across the entire depth range, it can create a 3D scene within the persistence of human vision, with content placed at its appropriate depth, satisfying the eye's accommodation or the ability to focus. However, this time multiplexing relies on ultra-fast electronics. As the number of depth planes increases, the frame rate and brightness of the display have to inversely decrease. This recent result from our lab shows a display that is capable of showing 40 depth planes at 40 frames per second, but it also required a high-speed projector that has to operate at 20,000 Hz. In contrast, the proposed work produces virtual 3D scenes in an instant, at the native frame rate of the display. So how does Split-Lohmann lens work? To understand this, we need to go back to the 70s when Adolf Lohmann introduced the idea of his namesake lens, the Lohmann lens. A Lohmann lens consists of two cubic faceplates. In their normal position, the two cubic faceplates cancel out. However, when they are translated with respect to each other, they produce a lens. A Lohmann lens is a focus tunable lens whose focal length is controlled by their amount of relative translation, with greater translation producing smaller focal length lenses. Because it's a focus tunable lens, a Lohmann lens can be used to create a multifocal display. So now let's start with a basic design of a multifocal system, but now translating the display instead. The virtual focal plane is translated in depth. In an equivalent way, we can also use focus tunable lenses or liquid lenses to shift the focal plane as shown here. So in this configuration, changing the focal length of the lens in the middle optically shift the focal plane in depth to different depths. Since the Lohmann lens provides focus tunability, we can also use them in place of the liquid lenses. Now, translating the cubic faceplates allows us to move the focal plane in depth. However, this design not just requires mechanical translation, but it also relies on time multiplexing, which makes it worse than using liquid lenses. We'll show next that both issues can be fixed. We created an optical relay that equivalently allows the control of the focal plane depth. But this time, we're splitting the two components of a Lohmann lens. We place the two cubic faceplates into different parts of the optical system. With this optical configuration, the first cubic faceplate is optically stacked with the second one, resolving an equivalent pair of cubic faceplates, or the Lohmann lens, but split. By introducing a spatial light modulator, or an SLM in the middle, we can redirect light, or optically translate both cubic faceplates with respect to each other. When there's no phase pattern, or a constant pattern on the SLM, there are no relative translation between the two cubic faceplates. If we change the tilt angle, or use a linear phase ramp on the SLM, we effectively translate the cubic faceplate by some amount. If we increase the tilt, or the slope of the phase ramp, we translate them even more. Now recall that the Lohmann lens is a focus tunable lens. This tilt angle effectively controls the depth of the focal plane. By changing the tilt angle, or the slope of the phase ramp on the SLM, we can decide the amount of relative translation of the cubic faceplates, and consequently choose which depth to place the focal plane. Since the display is optically co-located with the SLM, for different local area on the display, we can choose a different tilt, and consequently, independently adjust the depth for individual pixels on the display. So with this idea, we can simultaneously place pixels to different depths. As an illustrative example, let's consider this scene with point light sources placed at different depths. To place each point at its appropriate depth, the pattern on the SLM here needs to produce a corresponding translation between the cubic faceplates. We use a different phase pattern for different area on the display, corresponding to each point. We achieve this by coupling the local tilt or the local slope of the phase ramp to the scene depth, using an appropriate analytical function. The resulting scene visualized here is an image captured from our lab prototype with the camera focused at infinity. Zooming in, we see that the dot at infinity is in focus, while the closer points get more and more out of focus. Here's our lab prototype. The optical design requires 2 cubic faceplates and multiple lenses, but in practice we can fold the optics to reduce the physical footprint. Our prototype reuses the same cubic faceplate. Like before, to create a 3D scene, we can take an RGB image and a depth image as input. We feed the RGB image to the micro OLED display and compute a face mask from the depth image and feed it to the SLM. Here's a focal stack captured through our prototype display from a camera that is completely untethered to the display. We see that content at different depths come in and out of focus. Our display is optimized to create scenes with depth spanning from 25 centimeters to infinity, with a field of view of 25 degrees and an eye box of 5 millimeters. These are design choices that result from choices of various optical elements that we discuss in detail in a paper. So let's now look at the spatial resolution limits for depth control. Recall this image formation model with a point light source on the display. Upon propagation to the SLM, the point light source is no longer localized to a point, but instead it takes the form of a triangular blur kernel due to the spread induced by the cubic faceplate. The size of the spread in our system is in the order of 50 microns, or 10 pixels on the display. When the depth is constant, or changes smoothly, the spread of this kernel is reverted back to a point by the second cubic faceplate. The point is then placed at one depth, and there is no artifacts. However, when there are sharp depth edges, different parts of the kernel experience different phase ramps. The net result is that the point will appear at both depths with split bokeh. Because a blur kernel is asymmetric, for a point that is at the same distance from a depth edge, the orientation of the edge actually determines the kinds of artifacts we get. So in one case, the artifacts are significant. In the other case, there are none. The idea of a spatially varying focal length lens has been explored before in focal surface displays by Masuda et al. In 2017. Here, an SLM is introduced between the display and the eyepiece. Consider now 3 points on the display. By creating lenses of appropriate focal lengths on the SLM, we can place each point at its different depth. Taking this idea to the limit, we get a technique that is similar to Split-Lohmann, where a lens with spatially varying focal length maps the display onto a smooth focal surface. The smoothness of the focal surface is tied to the cone of light emitted by the display and the pixel size of the SLM. So shown here are focal stacks captured from both prototypes of both displays. Focal surface displays on the left show significant artifacts in spite of time multiplexing 3 focal surfaces for this result. In contrast, our display produces scenes instantly without time multiplexing. It's also worth noting that this is not an equal comparison due to the basic differences in hardware. Since the display has a light computational footprint, it supports streaming 3D content from interactive programs as well. This is a session of the interactive 3D Minecraft game played, where the display and SLM input were generated in real time. Like before, we manually adjust the camera's focus to visualize how content come in and out of focus at different depths. A key limitation to our system is its large physical footprint. This is my colleague Wei-Yu carrying our binocular prototype. We believe that this can be reduced by avoiding 4F relays with polarization optics to further reduce the optical path length. In summary, Split-Lohmann provides an exciting new way to create a virtual 3D world. We have an e-tech demo at the SIGGRAPH where you're welcome to experience our display. Thank you.